The obvious application of universal gravitation is to look at orbits, so I'm going to do that. Let's say we have a planet. That was generous. And we have an object in orbit around it. Meant to be a satellite, I understand it looks more like, well, a TIE fighter. Here is the radius of our planet. And here is, there is going to be some altitude that this is flying. So that we can say that the distance from the center of the planet to that object is going to be r, which is the radius of the planet plus the altitude. This thing gets a mass of little m, mass of the spaceship. This gets a mass of capital M, mass of the planet. And maybe what I would like to know, the classic question to ask here would be to find the altitude at which you reach geosynchronous orbit. And I'll cover that in a moment. For right now, let's say we can find the speed of the ship as it orbits. Now this ship is going to make a circle around a circular orbit around this planet. Now I know that I have already labeled this R and everything, but I've got this nice yellow line for my circle, so I'm going to do that for my radius. So I'm going to start solving this thing. If I make it one time all the way around, then I have a path length, a distance that I've traveled of 2 pi r, which will be important. Let me look at a free body diagram for this mass. Now I'm going to move this mass from here to this spot directly above just so that my free body diagram can be vertical. I'm not going to actually move it, I'm just going to pretend that it's there. So here's my mass. It feels a force of that, F, gravity, and that's the only thing that it feels. So I'm going to call that my positive direction. When I write my sum of forces equation, it's going to be really simple. My sum of forces is Fg. Sum of forces equals mass times acceleration. So that's a good start. My Fg, I am looking at gravity and I'm definitely looking at a large scale. When I think orbits, I'm thinking this is a large scale. So that gravitational force is going to be G times the mass of the planet times the mass of my ship divided by r squared. That's the first part. The acceleration, I am moving in a circle, so that centripetal acceleration is what that must be, and that's equal to v squared over r, which is great because v is what I'm looking for, so I had to introduce that somewhere. I will also say, so this is going to be equal to m times v squared over r. A lot of times when I write centripetal acceleration, I like to write my r as a capital R. It's just a preference thing. It's just something I kind of got used to doing once upon a time. The r is the radius of the path you're taking, so we do need that yellow little r. So I can solve this thing for v. First I can cancel my masses, that's good. I can cancel an r, and that's pretty nice. And I get g times m over r equals, let's throw a square root on that thing, equals the speed. That's nice too, and I can do this to find the speed of the ship. What if I were asked to find the time for one orbit? So, question 1, find the speed of the ship. Done. There's question 1. Question 2, find the time for one orbit. I can say that my speed is going to be distance over time. And that means that my time is just distance over the speed. I just found my speed, and my distance, like I said, was going to be 2 pi r. 2 pi r over the speed, gm over r square root, and I've got the time for one orbit. I can do a little bit more with this, and that's the idea of geosynchronous orbit, which is a different problem, but it's related, so I'm going to do that too. Let's say I've got this same thing, this same planet, and now what I'm looking for is, and now we will switch and call this thing Earth. We didn't call it anything before, but let's call this thing Earth. I would like to find the altitude for geosynchronous orbit. So I should talk for a moment about just what geosynchronous orbit is. Geosynchronous orbit, we use this for satellites. It is the idea that there is a spot on the surface of the Earth and that we have a satellite that stays directly above that spot. This is really helpful for navigation and for setting up any kind of signal relay, right? Because you know where that satellite's going to be at any given time. So what you can almost think of this as, and this is maybe a good way to picture it, if we had a really tall tower on the Earth, the satellite would just sit on top of that. So when the Earth makes one full rotation, the satellite has made one full rotation. It's always directly above that spot. That's what a geosynchronous orbit is. We are synchronized with the geo, with the Earth. So now we're going to find the altitude for geosynchronous orbit, and that altitude, there's only one altitude for it. It's different depending on the planet, right? If you wanted to do this around Mars or something, then we would have a different altitude, but for the Earth, there's only going to be one. That means that what we are looking for is H. Hexagon, sure. What I would like to solve for instead is R. Once I've got R, I'm going to use this equation right here to solve for H, because solving for H directly is going to be ugly and messy, and I don't want it. So here is my satellite. It has a gravitational force acting on it, and that's the only force. So I'm going to again call that my positive direction. It's got a mass of m, which is really descriptive. And so I get a sum of forces equals Fg. It's the only force I've got, and that's going to equal mass times acceleration. Fg, again, is going to be g times m times little m over r squared. R is my unknown now. I'm going to set that equal to mass times, and again, my acceleration is going to be a centripetal acceleration because I'm moving in a circle. So I'm going to get a v squared over r. I can cancel an r, that's kind of nice. I can cancel an m, that's kind of nice. But for geosynchronous orbit, do I really know my speed? Yes and no. What I do know is that one full rotation is going to take me 24 hours. So my speed, I know, is going to be 2 pi r divided by t, where t is 24 hours for the Earth, so 86,400 seconds. Cool. I've got enough information now. G times mass of the Earth over r equals, when I take v and square it, I'm going to get 2 pi r over t, and I'm going to have to square that. I'll just do that in my next step. And then the over r part canceled out, which was great. Now squaring this. I need to square each term in there, so the left side stays the same, gm over r. And the right side becomes 2 squared is 4, pi squared is pi squared, r squared is r squared, and t squared is t squared. I now have an equation that only has r as an unknown. So I'm going to solve. I'm going to multiply this side by r to cancel that out, which means I multiply this side by r. I'm going to multiply by t squared to get rid of that. And I'm going to divide by 4 pi squared to get rid of that. So that leaves my left side as g m t squared over 4 pi squared. And it leaves my right side. I had an r squared, I picked up one more, so that's going to be an r cubed. Which means my r is going to be gmt squared over 4 pi squared, all to the 1/3 power. Still not quite the value that I'm looking for. Remembering all the way back to the beginning how I said what I was looking for was that h. I need to find what my h is. From here, I can say my height, the altitude, the distance above the surface that the satellite needs to be, is going to be gmt squared over 4 pi squared, all to the 1/3 power minus the radius of the planet. This is just saying I'm solving for that altitude, so I want the distance off the surface. My whole equation over here, my gravitational force, gives me the distance from the center, so I just need to subtract off the radius of the planet. That's my height for geosynchronous orbit. I made no assumptions when I plugged this thing in at all. I didn't actually plug in my 24 hours, I just said I know the orbital period, the rotational period for this planet. And I didn't plug in what the mass of my planet was or the radius of my planet, so this equation works for all planets. If I want to do this for the Earth specifically, now I need to start plugging in some values, and I can say my mass, my radius, and the time. The mass of the Earth is 6 times 10 to the 24th kilograms. It's like 5.97 something times 10 to the 24th kilograms. The radius of the Earth is 6.4 times 10 to the 6th meters. And the time for one full rotation is 86,400 seconds, which is 24 hours. When I plug all those values in, I get an altitude of 3.5 times 10 to the 7th meters. That is the altitude above the Earth's surface for geosynchronous orbit for Earth. That's it. That's the whole thing worked out and with an example, all in one.